So if you have your device out right now, put it away. If you got phones out, put them away. All right, let's see. Today is October 16th. And today we get to talk about complex numbers. So first of all, we're going to do a quick review. We're going to solve these first few problems. Number 1 and 2, we're solving by square roots. So let's go ahead and do these real quick. So first thing we need to do, subtract 7 from both sides. That'll be 3x squared equals, what is that, 24? Divide by 3, x squared equals 8. And then x would equal positive and negative, the square root of 8. What would the square root of 8 simplify to? That would be the square root of 16. 2 root 2, yeah. If you take a look over here, if we take a look at the square root of 8, so the square root of 8 would be equal to the square root of 4 times the square root of 2. Square root of 4 is 2. Keeping the square root of 2 underneath the square root symbol, we get x equals positive and negative 2 root 2. All right. Next one over here. Everything inside the parentheses you can basically treat as the variable because it is being squared. If it's squared, that means it is a perfect square. So there's no use in expanding this. So we're just going to start by getting rid of the negative 3 that's being multiplied by the parentheses. So divide both sides by negative 3. So that'll be x minus 3 squared equals 4. And when we get to here, now we can square root both sides. And when you square root something being squared, you are left with whatever was underneath it. So we get x minus 3 equals positive and negative 2. Because the square root of 4 is 2. This is going back a couple of weeks, and probably last week as well, because you looked at solving by square roots again last week. So we have to write 2 equations now, because x is not yet by itself. So we're going to say x minus 3 equals 2. X minus 3 equals negative 2. And then solve both of them by adding 3. Yeah. We divided by negative 3. Yeah. Because it was attached by multiplication. Yeah. So like if it was negative 3 plus the parentheses, then we would have added it. But because it's being multiplied, we have to get rid of it by dividing. Good question. All right. Add 3 to both sides here. 2 plus 3 is 5. Add 3 to both sides. Negative 2 plus 3 is 1. So you can write this in set notation if you want to, or you can just write it like the line above, x equals 5, x equals 1, or you could write it as x equals 1 and 5 in set notation. Either one of these is fine. You can leave them separate, or you can put them together in set notation. And by the way, the reason why we use braces here instead of parentheses is because braces indicate the same value. These are both x values. If you have parentheses, that implies you have an x and a y as a ordered pair. But these are not an x and a y. They're both x's. All right. Next one says to, again, use square roots to find the zeros. All right. So very similar. By the way, we're finding zeros here. So if we're using square roots, then essentially this f of x is our value of y. It's going to equal 0, and we have to basically do the same thing. So we're going to start by adding 15 to both sides. So that'll be 15 equals 3 times x plus 2 squared. And then we're going to divide by 3. So that'll be 5 equals x plus 2 squared. Square root both sides. So that'll be positive and negative. Square root of 5 equals x plus 2. Kind of out of room here, so let's see. Use some room over this way. I'm going to flip the whole thing around now. I'm going to put the x plus 2 over on the left, and the positive and negative square root of 5 on the right. So this will be x plus 2 equals the square root of 5, and x plus 2 equals the negative square root of 5. And we'll go ahead and subtract 2 from both sides. So that'll be x equals negative 2 plus the square root of 5, and x equals negative 2 minus the square root of 5. This is all stuff that we did a couple of weeks ago when I was still here. And then we can actually put these two together. to write them as one answer because they both have -2, and we have a positive and a negative square root of 5. So we can just say x is equal to -2 plus or minus the square root of 5. And just write it like that. All right. And then the last warm-up question, solving by square roots. Start by subtracting 18 from both sides, because we're basically saying this thing equals 0 before we start. So that'd be -18 equals -2x squared. Divide by -2, and then 9 is equal to x squared. Square root both sides, so x is equal to positive and -3. There we go. So that's everything that we got there. And we do get to review one more problem, and this is the falling object model that we're going to look at with number 5. Any questions on those first 4? I know that was very quickly through those 4, but you've seen solving by square roots twice over the last week and a half now, so hopefully this is okay at this point. All right, number 5. A student designs a case to prevent a cell phone from breaking when dropped from a height of 30 feet. Wow, I want that phone case. Actually, I don't know if I do. It'd probably look a lot like an OtterBox, and those tend to be kind of chunky, which kind of defeats the purpose of keeping things slim. So I don't know. What's that? Yeah, basically. Or maybe it's like the egg drop thing, and they designed a parachute into it. All right. Hey, so we go to write a function that models the height in feet of the container after t seconds. So here it is. Use the form h of t equals -16 t squared plus h of 0. So, or h sub 0. So how long does it take the container to hit the ground round to the nearest 10? Bonus. Find and interpret h of 0.25 and h of 0.75. Or wait, 0.25 minus 0.75. Oh, interesting. So what do we think here for this first one? What is h of 0 going to be? What's that? 30, yeah. What does h of 0 mean? Or h sub 0, not of 0, h sub 0. What does that 0 mean? Any thoughts? Was that taught last week at all? What the number means? What's that? Nobody taught you what that meant? Okay. So the sub 0 just means h with an x value of 0. So the height, x value being 0, would be a time of 0. So the height when time is 0. When the time is 0, that's like when the experiment starts, right? So what's the height of the phone at the beginning of the experiment? 30. Yeah, because it's dropped from a height of 30 feet. So before the experiment starts, it's starting up here at 30 feet. The experiment has not started yet. It's at 30. And so then it drops and it ends up at a height of what when it hits the ground? 0. Okay. So the function we're going to write for A is going to be 0 equals -16 t squared plus 30. And then we're going to solve for t using square roots. So in terms of the height, we know it's going to be 0 when it hits the ground. It started from an initial height. This is the starting value, basically, the initial height. That's all that means there. So now we're just going to do what we did on the first 4 problems. So we're going to subtract 30. That'll be -30 equals -16 t squared. We'll divide by -16 on both sides. So that would be 30 over 16, which would be, those are each divisible by 2. So 15/8. Does that sound right? Okay. So 15/8 equals t squared. By the way, we're working on part B right now. This is part B. Solving it is part B. So let's see. I'm going to move. Well, we're going to a little bit of space left. So that'll be. I'm just going to go over here. So I'm going to say t squared equals 15/8. I'm just going to swap the whole thing around. And so we need to square root this. So that would be t is equal to the square root of 15 over the square root of 8. But we said earlier that the square root of 8 is equal to 2 root 2. So I'm just going to say 2 root 2. Okay. Now we are not allowed to have a radical on the denominator. So we have to rationalize the denominator. What do we have to multiply by to rationalize this denominator? What's that? Yeah. We can multiply by 2 radical 2, or I think we could just multiply by radical 2. Because that would also just get us whole numbers on the denominator. We could do either way, but I'm going to say just radical 2. So root 2 over root 2. Because the square root of 2 times the square root of 2 on the denominator is 2. And then multiplied by that 2 would be 4. So we're going to get t equals, the denominator now equals 4. And the top is equal to the square root of 30. Because 15 times 2 is 30. Are there any perfect square factors of 30? 4, 9, 16, 25. That would work for 32. So it doesn't look like it. I think radical 30 kind of is what it is, root 30. Root 30. Oh, okay. And plus or minus. Don't forget the plus minus. And then from there, okay, from there, we are going to round to the nearest 10th, because that's what it tells us to. So let's see, fraction root square root of 30 divided by 2 equals about 2.7 seconds. Now, quick question for you. The positive and the negative, should we include the negative here? Why not? Negative time doesn't make sense. Yeah, it's not going to take negative 2.7 seconds for the cell phone to hit the ground. It'll take about 2.7 seconds. So we're going to say t is approximately 2.7 seconds. So that's about how long it's going to take the phone to drop to 30 feet to hit the ground, and hopefully it survives. All right, now let's see. The bonus question. Find and interpret h of 2.5 minus h of 0.75. Or sorry, 0.25 and 0.75. Basically what that means is we're going to take our original function, this one right here, and we're going to plug in 0.25 for t. And then we're going to take our original function and plug in 0.75 for t, and then figure out the difference of those, and then kind of try to understand what that means. So h of 0.25 is going to equal negative 16 times 0.25 squared plus 30. That's what we're going to start with, 0.25. So let's see, negative 16 times 0.25 squared plus 30 is 29. What does that mean? What is h of 0.25 equaling 29? What does that mean? What number did we plug in 0.25 for? What variable did we plug it in for? T, right? So what does that mean for t? 0.25, what does that mean? 0.25 seconds, right? A quarter of a second. And then the 29 is what? The what? Yeah, the height. So that means after a quarter of a second, the height is 29 feet from an initial height of what? 30. So a quarter of a second, it has dropped by 1 foot. That's what we're saying so far. Now, after 3/4 of a second, 0.75, let's do that. So h of 0.75. Negative 16 times 0.75 squared plus 30. So I'm just going to go back and use 0.75 instead of 0.25. And that's 21. So equals 21. So that means at 3/4 of a second into its fall, it is now at 21 feet. So it takes 3/4 of a second for it to drop 9 feet. So if you take the difference of those two things, the answer for 0.25 and the answer for 0.75, and you subtract it, what do you get? 29 minus 21, that's what this is. 8, okay. So that means between the half second, in between 1/4 of a second and 3/4 of a second, it dropped 8 feet. That's what that means right there. So anytime you're interpreting, by the way, a problem like this, find out what you're plugging in for. Figure out the variable you're plugging in for, and that's going to tell you what that means. So 0.25 for t means 1/4 of a second. 0.75 for t means 3/4 of a second. And the value after that is going to be the height that it is after that amount of time from its initial height. All right. So if you were a little unclear about the falling object model, hopefully this kind of clarifies it a little bit. All right, let's turn the page. Today, we get to learn something new. We get to learn something like real new. This is new. This isn't like Algebra 1 new. This is like Algebra 2 new, brand new. All right. So the imaginary unit. We already know that sometimes you can't get a real number answer because sometimes you have a negative number that you try to square root and that doesn't work. So not every quadratic equation has real solutions. For example, x squared equals -5 does not have, that got hole punched out, does not have solutions that are real numbers. Graphing y equals x squared plus 5 shows no x-intercept, so we can confirm that there are no real solutions. X squared plus 5, by the way, is an upward-facing parabola, but it's above the x-axis, and so the vertex is at the bottom, but the bottom of the graph is above the x-axis, which means it does not have any intercepts with the x-axis. To fix this problem, mathematicians created the imaginary unit. So this was originally something that was created, but then it was discovered later that it's actually useful. A lot of stuff in math initially is just done as more of like a thought experiment. People are just trying to reason their way through something. And then oftentimes years after those things have been theorized and like worked with, somebody else comes along and actually finds a practical use for it. That happens a lot in math. So, and that is what happened in this case as well. I don't know the timeline on it exactly, but it's defined as, the imaginary unit, by the way, is defined as I. And I represents the square root of -1. And it expands the number system beyond real numbers into imaginary numbers and then complex numbers. And so now we can find the square root of negative values. So, are we all ready for this? This is good stuff. So, first of all, the thing I want you all to know is that, and I mentioned this before, the imaginary unit, that little I being congruent or equal to the square root of -1, we're essentially, it's not actually a variable, but we're going to treat it as if it was a variable because I think it makes it easier to understand in that way. If you got this little I hanging out there and you're trying to think of it as the square root of -1 the whole time, your brain might explode because trying to think of the square root of a negative number doesn't really work, and that's the whole point of this. And so if you try to really wrap your mind around why that is, it's gonna make your brain melt, and that might not be very comfortable. And if you consider it more of as a variable and you work at it and you work with it like it's a variable, that tends to make things a lot more smooth sailing. So I'm going to encourage you to think of I as more of a variable than anything else. So first of all, it's saying that if R, so here we go. Here's some just sort of math definition stuff, and then I'll kind of unpack it and help you understand what all this means. So it says if R is a positive real number, then the square root of the opposite of R is going to be I times the square root of R. For example, if you try to take the square root of -3, you can't do it. But if you separate it out, first of all, there's an in-between step here. If you separate this out, go ahead and do a little arrow up here into the square root of -1 times the square root of 3, because -1 times 3 does equal -3. That's a fact, we know that. And if we're saying that the square root of -1 is equal to I, which is the imaginary unit, then we end up with that. We just turn the square root of -1 into essentially the variable I, And then we keep the square root of 3 as the square root of 3. And so the square root of negative 3 turns into I root 3. Now, there are properties over on the left that I'm going to talk about real quick, and then we can come back to this one in just a moment. Are there any questions about this reasoning here, though? Anytime you see the square root of negative 1, you can turn it into I. And if you have a negative square root of something, all you have to do is separate that square root into negative 1 and then whatever else was over there. So basically, you take the positive value of that number and then negative 1, turn the square root of negative 1 into I, and then just keep the positive value. And if you can simplify the radical that's still underneath there, do that. But in general, you're basically turning the square root of negative 1 into a variable. All right. Now, there are some properties over here that I want to talk about before we look at number 2. And then we're just going to go through and do some simplifying. And then after that, we're going to talk about some complex numbers. So here we go. The important identity here is that I is equal to the square root of negative 1. Those two things are interchangeable. So if you see the square root of negative 1, make it an I. However, if you think about this for a second, this is where things get a little bit odd. If you square I, that would be the square root of negative 1 squared. Yeah? Because if I is equal to the square root of negative 1, then I squared would be the square root of negative 1 squared. Everybody okay with that? Okay. So this would be the square root of negative 1 squared. Now, correct me if I'm wrong, but the square root and the square are inverse operations, right? They undo each other. Yes? So when you square a square root, you're left with the thing that's under the square root. So what does I squared equal then? Negative 1. This is kind of a weird thing. Because when you square an irrational, or not an irrational, when you square an imaginary number, you end up with a real number. Squaring an imaginary number results in a real number because the squared and the square root cancel each other out. Think of it another way. The square root of negative 1 squared is equal to the square root of negative 1 times the square root of negative 1. Which would actually just be 1 now that I'm thinking about that, but it's not 1, it's negative 1. So forget that I said that. Because this is negative 1. Undo it. All right, how about the next one? How about to the third power? Let's just go ahead and use negative 1 as our, because I to the third power, can we agree for a second that this would be I squared times I? We break it apart, I squared times I. Yeah. So I squared is negative 1, isn't it? Okay. So this would be equal to negative 1 times the square root of negative 1. And this is equal to the square root of negative 1 is just I. So I'm going to change that back to I real quick. So this would be I times negative 1, but anything times negative 1 is just that thing as its opposite. So this would just be negative I, or the opposite of I. What's that? No. It's the opposite of the square root of negative 1. Yeah. The opposite of the square root of negative 1. Okay. Let's try the power of 4. So the power of 4 would be I squared times I squared, yeah? And I squared is -1 times another I squared is -1. So what does that equal? It equals 1. So we've got +1 now for I to the 4th power. All right, let's keep going with this. There, you're going to see a pattern developing, by the way. So we got I squared is -1, I to the 3rd is I to the 4th is 1. Let's keep going here. So I to the 5th power. Let's see, we know that I to the 4th power is 1. And then I, so this would be I to the 4th times I. And if I to the 4th is 1, and we multiply 1 by the imaginary unit, 1 times anything is itself. So that means that I to the 5th power is just I. So this means we're back where we started, right? Yeah. Let's go back here for a second. So this is basically I again. So if we kind of think about this pattern, if we go to I squared and I to the 6th power then should probably be the same thing. So this would be I to the 5th power times I, because that's what I to the 6th is. Which would be what? -1 again. Yeah. So I to the 5th power is I times I, which would just be, since I to the 5th is I, then we'd have I times I, which is equal to I squared. But I squared is just -1, so that's -1. So I to the 2nd and I to the 6th are the same. I and I to the 5th are the same. So I to the 7th should be the same as I to the 3rd, which is what? -I. And then I to the 8th would be 1. So that pattern repeats itself. So basically, all you need to pay attention to here are between I and I to the 4th. If you add 4 to any of these exponents, it's going to be the same as the one that it is in the first place. So if you add 4 to the exponents there, that's I to the 5th. It's the same as I. So it goes in cycles of 4, basically. If you add 4 to the exponent for each one, you get the same thing. All right, let's do some simplifying here. A. We'll be able to practice this as we go through here. So A, square root of -25. Let's go and expand that real quick. That would be the square root of -1 times the square root of 5. The square root of -1 is I. Oh, that's 25, sorry. Times the square root of 25, which is 5. So this would be I times 5 or 5I. Generally speaking, because we're using the square root of -1 as a variable, we write variables after numbers, therefore 5, and then times the square root of -1, which is I, so we get 5I. 25 square roots to 5, square root of -1 square roots to I. This is 5 times the square root of -1. Questions about that? What's that? The negative square root? To be honest, I don't know. But I know it's useful for electricity. Yeah. There are calculations that have to do with like the flow of electricity, I think, that actually use the imaginary unit that make it useful for.
Now that you mentioned it, it's still a lot.
Yeah, what does your brother do? Is he an engineer student?
Yeah.
Yeah, electrical engineer. Yeah. So, yeah, the imaginary unit is very useful for electricity. I am not on the practical side of it. I'm on the theoretical side. So, like, I understand like the theory behind this, but I don't really understand how it's applied necessarily. But it's out there. Yeah. All right. Let's try B. So what we're going to do is we're going to separate these out. We're going to take the negative square root of -1 times the square root of 72. And then all we're going to do is simplify the square root of 72, like we did last week and the week before. So we're looking for the largest perfect square factor of 72. Six is in there, 9 is in there, there's a bigger one. 36. 36 and 2. Yeah. So this would be the square root of -1 times the square root of 36 times the square root of 2. And so the square root of 36 is 6. The square root of -1 is the imaginary unit. And then the square root of 2 remains the square root of 2. We get 6i root 2. Any questions about that?
Like say, like 36
In terms of,
side.
oh, it would be like this first one. Yeah, that means if there's two of them, that means the number is a perfect square. Yeah. Because if it was 6 and 4, then the number underneath there would have been 144, and 144 is a perfect square. All right, let's try C. Okay, everybody take a look at C. Here we go. We got -5 times the square root of -1 times the square root of 9. 9 is a perfect square. 9 square roots to 3. Yeah. Okay, so that'd be -5 times 3 times the square root of -1, which is the imaginary unit. And then we can multiply -5 and 3. Because those are just regular numbers to multiply. So we get -15i. What's that? The square root part, yes. But the number that was out here was already negative, which is fine. Negative numbers are fine. It's just that negative radicals are not, or not radicals, negative square roots. Negative radicals in general are generally okay. It's the square roots a lot of the time. Okay. Any questions on those three? Because I'm going to have you try the 3 at the bottom on your own. Yeah. All right, give it a try. 1, 2, and 3, go for it. And by the way, if the order of this is kind of messing with your head a little bit, you are welcome to do. You're welcome to write it like that instead and do the square root of -1 afterwards. And then just simplify them in that order. That would be fine. All right, go ahead and take a look. So number one, 9i. Number two, 2i root 14. And number three is negative 14i root 3. Any questions on those? Which one, number two? So 256 has factors of 4 and 14. 4 square roots to 2, square root of 14 doesn't simplify, square root of negative 1 is I. So it'd be 2i root 14. So it's always the regular number, then the imaginary unit, then whatever's left over under the square root. So that's the order that we're going to write things in. All right. Questions on those? I don't see any hands up. All right. Does anybody need more time to write these down? Okay. Give you a little more time here. I think moving forward, we get to talk about some complex numbers. What's that? Does it sound complex? All right. Wow. Good. All right. Flip it on over. So the previous examples used imaginary numbers, which are numbers that use the imaginary unit I. Complex numbers are complex because they have two parts. It's basically like a binomial. Think of it like a binomial. It's written in the form of a plus bi, where a is your real number. That's the part of the number that is the real number. And then the imaginary part is bi. So whatever number goes along with that imaginary unit. And you can think of these like binomials, whereas they are not like terms, right? You got an imaginary number here plus a real number here. Imaginary numbers and real numbers don't add together. So it would be like trying to add 2 plus 3x or 9 minus x. They have to stay separate. So if you think of these as binomials, again, continue to think of I more or less as a variable. And then this last one here, 5/3, that's a fraction, which is real, plus the square root of 2 times I. Probably should go with I root 2 on that one, instead of 2 times square root of 2 times I. But in general, they are in the form of a plus bi, where a is your real number, and then b is the imaginary part of that combination. So basically, complex because it's a combination of a real number and an imaginary number. So next thing we got here, find the values of x and y that satisfy the equation. So now we are looking for two numbers, x and y, that work with this. It's going to be a little bit weird, yeah? Let's look at that for a second. Okay. So essentially what's going to happen here is you're going to take the parts of this equation that are real and write an equation out of that. And then you're going to take the parts that are imaginary and you're going to write an equation with that, and you'll be able to solve for x and y. So for example, the parts that are real are here and here. And the bits that are imaginary are here and here. So if we have our two separate little equations, we've got our real and we've got the imaginary. And for the real part, we're going to say 2x equals 10. And the imaginary part, we're going to say negative 7i equals y times I. And we just solve those. What does x equal? 5. Yeah, just divide by 2, x equals 5. Any thoughts on the imaginary side? Why is that? Yeah. We can divide the I out of it because we're trying to get y by itself. The thing that's multiplying by y is I, which is the square root of -1. So if we divide by I on both sides, that'll give us -7 equals y and x equals 5. And if you think about going back here, what is 2 times 5 over here? 10. So this would be 10 minus 7i equals 10. What did y equal? -7 minus 7i. There you go. You can substitute them back in, make sure they work, and look at that, same number. Same complex number on both sides. So let's try the next one. 9 plus 4yi equals -2x plus 3i. So take your real number parts, -2x and 9, write an equation. So -2x equals 9. Divide by -2, what do you get? -4.5, yeah, -4.5. Set your imaginary parts equal to each other. 4yi equals 3i. What are we dividing by here? We will divide by I and by 4. Because y, the variable here, is being multiplied by both I and 4. So we can actually just divide by 4i and just do everything in one step. So 4's cancel, i's cancel, and then you get 3/4, which is the answer, or 0.75. There you go. Try the next one on your own. Set the real parts equal, solve for x. Set the imaginary parts equal, solve for y. This one should be easier than number 4, by the way. What do you have, x for number 5? 7, good. How about y? -20, good. There we go. It's basically just asking yourself, like, look at the 35 and look at the 5x. What number times 5 equals 35? Well, that's 7. How do I get -20 over here instead of y? Well, you just replace y with -20. Good. So it's almost like direct substitution. Essentially what ends up happening here. Questions on those? Cool. All right. Now we get to add and subtract with complex numbers. So this is basically combining like terms. I'm just going to write that. Combine like terms. You all know how to do that, right? So if you're adding two complex numbers together, we have 8 and 5. Add those together. What do you get? 13. If you have a -1 imaginary unit and you add to it 4 imaginary units, how many imaginary units do you have? 3. There you go. That's the answer. 13 plus 3i. Now there's a hint underneath here, because whenever you are combining like terms and you have subtraction with that second set of numbers, you have to distribute the negative. This doesn't change how we do any of the math that we've learned how to do previously. We're just kind of adding on to the things that we already knew how to do. So if you distribute the negative, that would give you 7 minus 6i minus 3 plus 6i. And essentially, you just combine your like terms. What do you get on this one? 4. because the imaginary units cancel each other out. So sometimes two complex numbers result in a real number. All right, this last one, distribute the negative. So 13 minus 2 minus 7i plus 5i. What are we going to get? $11, close, minus 2i. Because the 7 was the further from 0. But yeah, 11 minus 2i. Good. This does look and feel exactly like combining like terms, yeah? Hopefully. Good. So far, decent-ish. Right. Couple more problems. Let's go and flip it over. Any questions on these three? Great. All right, let's keep going. Three more here, and then we're going to do some multiplication. So let's do these three very quickly. I'm not going to have you do these on your own. We'll just do them all together because they're super quick. So let's see, 2 plus 11 is 13. 9 minus 1 is 8, so 13 plus 8i. That's that one. Then we're going to have to distribute a negative for the next one. Or you can just, subtract. 13 minus 8 would be 5, so that's 5. And then 4 minus 4 would be, well, that's 0, so that number 7 is just 5. And then this last one here, let's see, 16 minus 13 is 3, and then negative 6 plus 8 is positive 2, so 3 plus 2i. All right, nice and quick for those. Okay, now we need to go back and think about some of those rules that we learned earlier with the I squared, I to the third, I to the fourth, all those little rules that we had, because we are now multiplying. So there's some rememberings over here. I squared is equal to -1. You also have up here, when simplifying an expression that involves complex numbers, be sure to simplify I squared as -1. It says twice, so that's probably an important thing if it says it twice. So here we go. Distributed property. So that'll be 4i times -6. All you have to do is multiply. This is like multiplying numbers and variables. Multiply the regular numbers together, -24. Put the variable or the imaginary unit at the end. Okay, -24i. And then if you multiply 4i times I, this would be plus 4i squared. Because I times I is I squared. However, I squared equals what? -1. So this would be -24i plus 4 times -1. 4 times -1 is -4, right? But with the complex number form, this is still a complex number, but now the real number's at the end, and the imaginary part's at the front. So we need to flip it around to get the real number at the front. So that's -4 minus 24i to get it into that standard complex number form. Any questions about that? So there's a little bit more to do once you start multiplying, because like I said, you can't just think of I as a variable, but you can think of it mostly as a variable most of the time until you start squaring it, right? So you start applying exponents to it, and then it actually turns into a number in a lot of cases. What do you think we have to do with B? Binomial times binomial uses what? FOIL. Use FOIL here. So first, 9 times -4, -36. Outer. 9 times 7i would be plus 63i. Inner. -2i times -4 would be positive 8i. And last, -2i times 7i would be -14i squared. Which would just be positive 14, right? Because I squared is -1, and -1 times -14 is positive 14. Okay, so that would be -36 plus 63i plus 8i plus 14. Now we have two sets of like terms here. We got negative 36 and positive 14 as our real number portion of our complex number. So negative 22. 63 plus 8 is 71. There we go. Negative 22 plus 71i. All right, I'm going to stop there because we only have a few more minutes. I will answer these last two. I'll put those on Google Classroom later.